welcome back from the break. Right, we are on to our third session of the day. We don't have just one, but we have 4 speakers from Compare the Market. We have Henry, Scott, Andrea, and Thula. So Henry is a senior data scientist at Comparethemarket.com, having joined 4 years ago following a stint as an army officer, then completing an MSc in intelligent systems. Scott is a data scientist at Comparethemarket.com. He previously worked within the financial sector, benchmarking energy contracts, and studied for a PhD in statistics at Imperial College London. Andre is a junior machine learning engineer. He was previously a machine learning MSc graduate. And Thula is a junior machine learning engineer at Comparethemarket.com with over a decade of experience in software engineering. If you could, please. Oh, you've got your mic, sorry.
Hello, I'm Henry, a senior data scientist at Compare the Market, as you've just heard, and I'm here today to talk to you about some of the data science we get up to, in particular how we've improved how we communicate with our customers. I'll do a bit more of an overview of that shortly, but first, who are we? So we're a comparison website, largely for insurance, particularly car and home insurance, but we have a host of other products too. We were founded in 2006 and have grown pretty rapidly, now being one of the leading comparison websites in the UK. We, of course, perhaps have the much-loved meerkats to thank for that in part. And this year we've also welcomed Carl the Wombat to the family, who you may have seen on some TV ads, blundering around. And along with furry mongooses and marsupials, we also have great rewards for our customers, such as 2-for-1 on meals and movies, and also discounts at Cafe Nero. All in all, we help customers save time and money, and also have a bit of fun, allowing them to compare a variety of products and get great deals. In terms of Compare the Market representatives here today, you have Scott and me from data science, and Thula and Andre from machine learning engineering. But actually, there are a lot more of us here at the festival, some down here on the front row in blue hoodies, and over there. So yeah, easy to spot, and please come and find us after the talk down at our stand where we can talk about some of the other projects we've worked on. I'll just touch on here how we work together at Compare the Market before we look at today's case study. Over the last couple of years, we've really moved to a squad-based operating model with squads focusing on improving different areas of the business. Each squad is multidisciplinary, so will include people such as data engineering, marketing, tech, analytics and insights, but of course also data science and machine learning engineering. And this has really helped us align and collaborate much more effectively when working on projects together. And what we're going to talk about today was actually the outcome of the first squad that was stood up, which actually had a huge number of contributors, including the consultancy Woven Light, but also Rob Spence, who was the main contributor from Compare the Market, but unfortunately couldn't be here today, so you have me. Right, on to the focus of the presentation. We're here to talk about how a data science project can get off the ground, some of the challenges faced that we faced, and how we dealt with them. The hope was that the format lends itself to being fairly generalizable, like any good model, so that it offers food for thought rather than being overly tailored to one domain. And the plan is that Scott and I will talk about how we got from an idea to a production-worthy model, and then Andre and Thula will talk about how that model was productionized. So yeah, I'll start with talking about how we identified a proof of concept for a new project with the new squad, with the squad itself actually being a bit of a proof of concept in itself as a way to operate. As is typically the case, we look to address a customer and/or business problem, and a lot of analysis and analytics was done using a host of data, including internal customer data and interactions, as well as market and customer survey data, to really understand where the customer problems were and also the business opportunities. And these were then prioritized. And shown here are some of the examples of business problems that we asked ourselves that really relate to customer marketing, but there are a lot more questions that we asked, and customer problems, crucially, that were looked at. And this process led to a proof of concept idea, essentially a proposal that was hypothesized to help customers, but also improve sales. And the word proof here really relates to the fact that It was a hypothesis and it needed proving through some kind of minimum viable product or MVP before it became standard business practice. So what was the idea we went with? Next best action, or MBA, had the goal of understanding when customers were in market for various insurance products and to use this to improve the relevancy of our customer communications. No one likes receiving irrelevant email, right? Like, hey, you bought a toaster last week, would you like to buy another one? No, thank you, unsubscribe. So by understanding better when customers are actually might be interested in a particular product, we could improve the relevancy and personalized communications with them better, which is, of course, a better customer experience. It also enables us to recommend products that a customer or someone might not have thought about purchasing through Compare the Market before, with the benefit being to the customer that it's normally the case they switch provider for a product they already own, such as car insurance, thus saving money. And all of that really helps to achieve Compare the Market's goal of trying to make financial decision-making more of a breeze. So we now have our proof of concept idea, but when dealing with modeling problems, we of course have to be very precise about what we're trying to model. Machine learning models must of course be constructed in very particular ways in order to train and provide useful predictions. For MBA, we needed to decide and specify what time period would class as a customer being in market for a particular product, i.e. how long the window of opportunity was to contact them. For annual insurance policies, it's often the case that a customer can switch provider within the last 30 days of the 12-month period. But it might be that customer behavior and our intended use of predictions means that we wanted a shorter time window than that. And yeah, it really led to this initial first identification of a target variable, which was the purchasing of a particular product within a certain number of days. And tied to this in a way was deciding which products we would include in the proof of concept, which will also affect the customers we would actually end up targeting. For example, do we want to be able to recommend all Compare the Market products to all customers, or particularly focus on one pair, such as recommending pet insurance to our life insurance customers, for example. Sorry, I've skipped ahead. Yes, as I say, we decided to keep things simple to begin with, and really look at this journey of recommending one product, say product A, to holders of another product, say product B. So really, it's a binary classification problem. And then the idea is that we would then add products incrementally and assess performance each time we did this. So with that decided, we could then determine which features that we were going to include in this project and in this model. And shown on the slide are some examples of various sources of data we used, but I'll come more into that process on the next slide. And then finally, we needed to determine how much historical data we wanted to use to train a model. As insurance policies often cover 12 months, and it's normally the case, or often the case, that a customer only needs one of those products, say car insurance, there might only be one purchase per customer of a product within a 12-month period. So we need at least 12 months worth of data, but how much more? And as ever, there's that trade-off between using more data versus potentially older data being messier, maybe having incompatibility issues with more recent data, and potentially masking the better signal from more recent data. Anyway, we now had our target variable, we had a set of customers we wanted to model, an initial data set and some initial features. So with that problem defined, we then iterated through a cycle of having a hypothesis, training a model that incorporated it, and testing the consequence. So a lot of a data scientist's time is of course, taken up with this process, and the diagram shown here is quite a big simplification with many more steps often being included in such a representation. but I think it nicely captures how pretty much all development changes can be captured by this cycle, in that, a hypothesis could mean anything from what model type do we want to use, to what additional features might be useful, how to deal with imbalanced or missing data, and so on. In terms of features, one thing we found to be really useful was holding hypotheses workshops or brainstorming whiteboarding sessions with individuals from across the business who really knew a lot about the particular products that we were including and our customers. And the aim was to collate as many ideas as possible about things that might either increase or decrease the propensity of a customer purchasing. And then we could go away as data scientists and try to find data that captured that relationship and then turn it into features. And overall, the approach was really to test new ideas quickly and innovate off the back of each. For MBA, a key question we needed to answer was what model type we wanted to use. Would it be tree-based or perhaps logistic regression to benefit from easy interpretability? In the end, we settled on CatBoost, a gradient boosting machine, given its high level of performance on structured data and the fact that we were using a lot of categorical variables, particularly high cardinality variables with a lot of unique values, and it has some clever machinery to deal with it inherently. So we have our target variable, we have a large number of explanatory features in the model that's gone through a lot of development, and this is where I now hand over to Scott to take us through some model evaluation and then how we built upon this initial proof of concept. Thank you.
Thank you, Henry. So we've gone through that cycle that Henry described, hypothesizing, testing, training, and now we've settled on that final configuration that ultimately we want to use. But before we do any of that, before we even look to productionizing, we want to be able to communicate those findings. Maybe not just to those within the data science community or the data science team that we have, but also to the wider business and the various stakeholders. So, and in particular, we want to be able to convey those ideas to those that don't have that same technical background that we might have. So you can see a bunch of statistics on this slide. A lot of you will be familiar with them, but for those who aren't, we as data scientists obviously have these various performance metrics that we can make use of and can easily call to in order to evaluate our models. So, and in particular, we might also evaluate our models on a holdout set or something, or a test set that has been been kept independent of our training. So for the case of MBA in particular, we have this binary classifier, and what we can use are threshold-dependent metrics, such as the confusion matrix that's highlighted on the right. The confusion matrix displays the frequency at which our classifier coincides with the truth, and from this we can obviously derive various other threshold-dependent metrics, such as the accuracy of the model, the precision and the recall, for example. But we might also want a more holistic view of the model. And so we might want to make use of alternative metrics such as threshold-independent metrics, such as the ROC or the receiver operator curve. And that's what's displayed on the left. So for a perfect model, it will plot a line that passes through the 0, 1 point on the unit square. Whereas a completely random classifier, one that's not able to really give any discriminatory power between the two classes, will have a line along y equals x. And typically, if you have a discriminatory model, their line will lie in between these two extremes, the random and the perfect. A perfect classifier, for purpose of definition, is something that can completely discriminate the two classes within any set you've given it. So this graph is all well and good, but typically we might want an individual number, and so a lot of you will already be familiar with the area under the curve, or the AUC, which is just the integral of the ROC curve on the interval 0, 1. And a perfect classifier, as you might be able to see, has a value of 1 for the AUC, a random classifier, a value of 0.5, and typically models sit between 0.5 and 1. Now, although we have those metrics, they're really good. Maybe they're easy to understand for us within the data community. But these metrics are, for those who may not have that technical background that we do, can be quite complex. They require technical definitions, and because of those technical definitions, they make it really hard to convey a message and to base intuition on them. And you have to always remember, we're not just presenting to data scientists, so we're going to be presented to stakeholders, to higher ups in the company. So ultimately what this means is we need alternative ways of communicating our findings that make them much more accessible across the business. So for MBA, given that it is a classification model, one approach that we found that was really effective was cumulative gains charts. And I think they've been quite popular also at a marketing level. So broadly speaking, for those that don't know what a cumulative gains chart is it plots if you have a set and you have some converters within that set or some positive cases, it will plot the percentage of positive cases as you move up the deciles based on the scoring that your model has given. So let's make that a bit more concrete with an example. Suppose for MBA we've scored 1,000 customers. And in that pot of 1,000 customers, 100 people have converted. So in the top 100 scoring customers, let's say there are 60 converters, that will be a cumulative gain of 60%. In the next decile, if we have another 20 converters, then the cumulative gain at decile 2 is 80%, and so on and so forth, until you hit the 100% mark. Now, for a completely random classifier, or the baseline, which is shown in orange, again, like the ROC curve, it lies along the y equals x. So in decile 1, it will just have 10% cumulative gain. Decile 2, 20%, and so on. And in order to evaluate whether the model is doing better than random classification, it literally sits just above, or should sit above the baseline. Now, we have this graph, but the reason we really liked it for MBA was because we can make different sorts of statements. For example, we can say that if we had contacted the top 50% of customers, we could have reached 94% of potential converters. And statements such as these make it much easier to understand and feel much more tangible, making it much more accessible across the business. And thus, by being able to utilize alternative communications such as this, we're able to better action as a business on them. In the case of MBA, we're helping to drive greater relevancy in our marketing communications. So we've shown that the proof of concept works by displaying and communicating our findings to not just the data science people, but also to those outside. But now the business might come to us. They might say, oh, how do you expand the model? How can we make it useful for different business purposes? And so in the case of MBA, we didn't just want to focus on when someone was in market for product B, given that they had already purchased product A. We wanted various other combinations, product C to product D to product A, all of these permutations. But not only did we want to focus on the cross-sell, we also wanted to look at renewals. So customers who came back to purchase the same product. And so with that in mind, we had two potential approaches that we considered at Comparethemarket. The first was, can we build multiple models for every different possible product pairing? Or can we build a single multi-class classifier? And these obviously have their pros and cons, and the pros and cons can be considered opposite sides of a coin. So the advantages of building multiple models can be considered the disadvantages of building a single multi-class classifier. So for the case of multiple models, the advantage of separating out everything means that we can have separate feature representations for each product pairing. So by this I mean the feature engineering can be specific to the product pairing that we want. Whereas obviously for a multi-class classifier, all the data has to go in as one. Again, we can also benefit from targeting very specific groups if we build out multiple models but because we can train the model on very specific customer bases and then understand very specific customer behaviors. That's not really all that possible with multi-class classifiers. On the other, we also, with multiple models, have multiple points of failure. So in a production setting, this is more of a software thing, but in a production setting, if we have multiple models, if one of them fails for whatever reason, we can still action on the remaining models and the scores that they might produce. Whereas if we have a single multi-class classifier, we have one point of failure. If it fails, then we can't do anything. We can't produce any scores, and that could be, that's obviously not a great thing. On the flip side, though, a single multi-class classifier would obviously take less time and effort to develop and maintain. So if you thought about MBA, we wanted it operational for about 7 products. And so if you did the quick maths, it would be 49 potential or up to 49 potential possible product pairings. And trying to maintain that many models, develop that many models, and then maintain it in production is going to be quite a challenge, especially given the size of the team at the time. In addition, building out multiple models might suffer from not being directly comparable in score. And so by this I mean, what we wanted, an end goal of MBA was, if I'm a customer, am I more likely to purchase home insurance or car insurance and be able to get these relative rankings? But if I have a score, let's say I'm scored by a car model and given 0.6, and then by a separate home insurance model and given 0.8, it's not necessarily the case that because I've received a score of 0.8 on the home insurance, I'm more likely to interact on home insurance than I am on car insurance. That sort of direct comparison is not entirely applicable when it comes to multiple models. Whereas this is obviously rectified, or is less of an issue with multi-class classifiers. And as a result of sort of taking these all into consideration, we decided that multi-class classifiers was the way to go with NBA in order to build out all these different product pairings. Primarily because the time and effort it takes to develop and bring to production, and given especially that we had a small team at the time, and that the time frame we were working to was quite tight. So we've expanded out the model now, taking it from that initial proof of concept. But one thing we need to make sure, and is important, is to make sure that the model during production is performing as expected. In particular, we might also want to ensure that it is robust to software and technical bugs. So in particular for MBA, we have a regular cadence of retraining the model. This allows us to obviously use the most recent data and ultimately maintain that relevancy that we need in the model. And with each retrain of the data, we can also examine how the model will perform on a holdout data set. So this holdout data set is generated, I previously said this, but independent of any training data, but also independent of any other processes that might come up during the model production pipeline, that being like a tuning of hyperparameters, for example. So what we can do is with this holdout data set that we've kept the same over every single retrain of the model, we can start to gather different performance metrics to get an understanding of how the model is performing live or how the model is performing over time with each retrain. And what we can start to do is create plots, like you see on the left. It's a very simple plot. It's some synthetic example. But across these 3 different products, over each model iteration, we can monitor the performance and obviously identify if there are any degradations in the model that will require further investigation. So, as you can see in product C, there has been some model degradation. And typically, when we see issues like this in our monitoring pipelines, they require further investigation, and in particular, require very bespoke solutions, typically because the cause is quite unique, typically. So an example for NBA in particular was during when international travel was severely restricted as a result of COVID. So COVID came in, international travel was restricted, and as a result, insurance for travel obviously fell, the volumes we weren't seeing prior to COVID. And what this meant is the model was still pushing out those same volumes of travel recommendations, but obviously that will result in a drop in precision. So what we did was, in order to rectify this, was incorporate COVID-related features. And that seemed to adjust for the issue that we had. So I've briefly spoken more sort of abstractly about the monitoring pipeline. And hopefully this diagram represents what we do in practice at Comparethemarket. In particular, there are some parts here that are still under development, but I'll sort of briefly talk through what we do in order to ensure that our models are maintaining performance. So as I mentioned, we have that holdout group on the left, and utilizing that holdout group, we can split the most recent data that we've collected. Sorry, I should specify, this monitoring pipeline is applied every time we retrain the model. So we've taken this data set, we split it out into three: the holdout, the training, and the test. We then do any modeling, we fit the models, we tune hyperparameters, and that gives us a staged model. And on this staged model, we can evaluate it utilizing that holdout group that we had already identified. We can then also compare it to the current model and test statistics there. And then ask the question, is this stage model consistent in some sense to the current model? And if it is, we can then promote it to production. Otherwise, we would keep the current model in production. Now, obviously, there are still some kinks that we're trying to work out or iron out here, but hopefully, this gives you an idea of how such a pipeline can help us continuously monitor the model and identify those early warning signs of degradation. So it's also typical that we don't just want our models to perform well in practice. We also might want to be able to explain the model. In particular, for MBA, we have Cat Boost, which, like many black box algorithms, can be challenging to interpret. And it's frequently hard to diagnose which features are the most important. And in particular, customers might actually begin to question why they're receiving certain targeted communications, and therefore request an explanation from us. And under GDPR, we are also required to explain the predictions of our data science models. So ultimately, what we need is a simple way to explain the model at a customer level. And to this, we make use of something called Shapley values or SHAP values. Now, some people here might be quite familiar with SHAP values already, but for those who aren't, SHAP values take ideas from game theory and try and apply them to understanding feature importance in machine learning models. In particular, they attempt to quantify the contribution of each feature of a consumer or a customer in the model to their predicted value. And we also benefit because SHAP values are model agnostic, that being that they can be applied to any sort of machine learning model. And so to demonstrate SHAP values, we have a simple example here where we try to predict the probability of purchasing home insurance based on 3 different variables. The first being, have they visited the website in the last 7 days? Are they an account holder? And have they got car insurance? So we fitted the model, and we've plugged in some an individual customer's data, and it's given us a propensity of 0.75. And what SHAP values allows us to do is break down the contributions of each of those 3 features to that 0.75 propensity. So it's determined that having visited the website in the last 7 days contributes 0.5, being an account holder contributes a further 0.2, and not having car insurance declines the score by 0.05. And then taking that relative to the population average all sums up to 0.75. And hopefully this highlights a really simple example of ways SHAP values can be used. And in particular, we can also aggregate over these SHAP values in order to identify which features are most important in the model, as well as analyze trends in the data. So we've gone through this journey as a data scientist from proof of concept all the way to production model, monitoring, and explainability. And we've had to jump through a few hurdles to get there. And as a result, and along the way, we've added value to the business. In particular, MBA now powers our cross-sell email campaigns, hopefully bringing greater relevancy to our customers, with the hope of improving that customer experience, and thus moving us closer to attaining our customer and business objectives. We've also identified various other avenues for us to pursue with data science in order to personalize our customer experience, and ultimately with the hope of making financial decision-making a breeze. So I'd like to thank you for your attention, and now on to machine learning, who will discuss how to productionize a model.
All right then, thank you, Scott. So now we'll be changing tracks a bit, and we'll be talking about the more engineering bits that we have going on here. So we've seen the business challenges that the data science team tackles in order to bring value to our customers. But now let's take a closer look at how we can do this reliably and at scale. We'll be looking at how the NBA model has been productionized. So here we have a broad presentation of how things work. The backbone of the productionization process is represented by the 3 workspaces that take the model through its life cycle. We have the development workspace, the non-prod workspace, and the prod workspace. The important thing to note about each of these workspaces is that they all share 3 important qualities. First of all, they have controlled access to our data storage. Secondly, they have access to on-demand cloud compute resources, which can be customized depending on our needs. And third of all, they have controlled environments in terms of software versions, libraries, dependencies, and the sort. So any project begins its life in the development workspace, where data scientists use data that they pull from our data source in order to experiment, develop models, or perhaps improve an existing model. After the model has been defined and the code has been written, it is then integrated within our code base on GitHub with the help of machine learning engineers, of which I'm one. Once this code has been successfully integrated, it then passes through a series of integration tests, automatically done so through our CI/CD tools, in order to make sure that the model that we have developed is healthy and can be reliably delivered to our customers. Once all of these tests have been passed, the model is then deployed to the production environment, once again with the use of our CI/CD tools. From here, NBA is free to send the correct message to our customers at the right time in order to make sure that their experience with CTM is as smooth as possible. But of course, this was not always the way we've done things here at CTM. No person is born learned after all. So as a retrospective, let's take a look back at how things were done in the early days, when industry standards were not as mature as they are today, around the mid-2010s. So in this schema here, you can see how we had things set up initially. As you can see, it's a much simpler setup. What we had is that we had data scientists write code on their local machines. So this is local development. And then pass this code up to machine learning engineers for productionization purposes. And this entailed integrating this code within our data science framework at the time, which you can see on the right-hand side of the slide. In terms of the framework at the time, what we had going is that we had Amazon Redshift as a data source, which, for those that do not know, it is a cloud data warehouse. And from here, we pulled data into AWS Data Pipeline, which served as our sort of training engine, where our machine learning models were trained. These trainings were triggered and controlled using AWS Lambda function. And after the model was trained, performance metrics and the likes were monitored using Amazon CloudWatch. Additionally, information about the model's health, if it had any faults, the history of its runs and such, were sent to Slack so our engineers could monitor the model's performance and the model's health and could intervene if needed. Now, the keen-eyed among you may have already noticed some problems with our setup here. Indeed, these problems can be classified in 4 broad categories, which you see on screen now. The first of which would be collaboration. The setup that we had actively hindered collaboration. The code being locally developed had to be manually passed on to other collaborators and to machine learning engineers when it came time to productionization. This, of course, caused some friction which did not help our development process. In a similar vein, the local machine development often led to inconsistencies between development environments on the local machines of the data scientists and the environments in production, non-production environments, or even the local environments of other collaborators. These two issues together led to longer and frustrating development cycles. The scalability of this framework was also very limited. The contribution of data scientists had to often be heavily adapted in terms of used libraries, the code's compatibility with the framework, and this, again, hampered our capabilities to carry out multiple projects in parallel, as it just absorbed more of our time and resources. As work was done on local machines, data had to often be pulled onto these machines, and this could pose a possible data governance issue. We do not want sensitive customer information to be spread out across multiple devices when you no longer need it for the project that you're working on. In addition to this, the framework was not really compatible with the agile ways of working, which further exacerbated the scalability and collaboration issues. So we needed to find a new platform that would meet the challenges that we faced. And now Tula will take us to the history of how we went about finding that platform. Thank you.
Right, so as the business was growing and the data activities were growing, we needed to find a system that would really enable us to move at scale. So we needed to find a platform that would help us work together collaboratively, that would help us scale, that would also help us with the data governance. So at the time, we decided to find a platform that would support this. So what we needed to do was look around at what we had, what was already available in the market. There were already a lot of vendors that were supplying these platforms. So what we decided to do is we approached a couple of them, trying to do some initial testing with them. So this helped us narrow down to very few vendors that we could sort of go deeply and try them out. So we went through this platform selection process, not just as ML engineers, but as a wider data team. So this process involved the BI team, the data scientists, the data analysts, everybody would come and use the system. So what we did is we had two vendors that we're going to try out. Databricks was one of them, and another one that we had in-house. We had to organize a POC and a hackathon. So for this hackathon, we had a score sheet. So for this score sheet, we were going to mark against how easy was it to collaborate on this platform, how easy was it to scale, how easy was it to support data governance and other requirements that we had. So we had this hackathon, and at the end of it, we had one platform that was going to support all the requirements that we had, and that was Databricks. So if you don't know what Databricks is briefly, it's a platform the way you can go from feature engineering to a fully deployed system, ML engineering alive. So what we found was, for us, it was addressing the challenges that we had on productivity, because like my colleague just said, it was taking a lot of time moving from one person's machine to the other, and the environments were not matching, and this was causing us issues and taking us a long time to build from idea to going to production. So we also had the advantage of collaboration on Databricks, where we can share notebooks and workspaces. So the other good thing that we liked about Databricks was we could segregate on the workspaces what data people had access to. You could also segregate by environment and have people collaborating in that workspace. What we also liked about it was that we could spin up clusters as needed, which supported our scalability challenge. We also could integrate it with already existing systems that we're using for our data platform and also AWS. So the other good thing that we liked about it was the Unity catalog. It was going to support our data governance activities through being able to assign data access to table level or even at an even greater granular level. This was going to help support our data auditing. The other good thing that the Databricks had was the feature store. So at the moment, what we used to have, the data scientists used to have to feature engineer for every project, that start from scratch, feature engineer this, and then, this was unproductive. But with the feature store, we're able to have a central feature store where whenever they start a new project, they're able to just go in there and get all the features that they need, and as requested as well. So what next for the ML team? So we're going to continue improving the current framework that we have. We're going to be looking into fairness machine learning to make sure that the products that we produce are fair to our customers and are not propagating any bias. We're also going to be using more of the workspaces as isolated environments where people can have restricted access to data and can work and collaborate well. We're also going to be looking at the input and output generic frameworks, which are going to support all the teams that we're supporting, like BI, data analysts, and data scientists. So they do not need to worry about what data sources their data is coming from. It's going to centralize the data for them, and they don't need to worry about where that data is going to go to. So this is going to increase their productivity. Going forward, we're going to be looking also at making sure we have machine learning explainability automated, so we don't have the data scientists worrying about all this monitoring. The monitoring is going to come built in on our platform. So this marks the end of our talk. Thank you very much for coming. We are